Hello guys and welcome to another video with Cass on the Maizuma channel. So today we're going to quickly talk about how logical gates work in Shenzhen IO. Alright, so here I have collected a bunch of examples that should be enough for you to understand how those gates work. And the gates are those components, those little components that you see in here. All of the rest are just support systems for me to explain how they work. So let's run a quick simulation here and you can see the first one already working. So the first one is called a NOT gate. It basically inverts a signal. So the switch here is off, and then because the signal is inverted, the LED or the LED is on. So click it. Now it's on, which means that the LED is off. So this is a simple one to understand. And on the sides here, I added this little table to explain how everything works in every case. So let's start with a simple one. So this is a NOT gate. When the input is 0, the output is 1. And when the input is 1, the output is 0. Simple as that. The next gate is the AND gate. So it has a result or a positive result when both or all of its inputs are turned on, because you need this input to be on and this input to be on for the output to be on. If you turn off any of them, then the output is turned off. So yeah, you need all of them to be activated, and this is reflected here in this table. So it has two inputs, input 1 and 2. And if you look at the outputs, it's always 0, except in this case here. So this is exactly what I said. When both inputs are active, the output is also active. In any other case, it's inactive. Those are very useful, and we will see more about that soon in this video. Next up, we have the OR gate. So the OR gate is simple logic as well. So if one of the inputs is active, or the other one is active, the output is also active. So yeah, you can turn both on at the same time. If you compare the OR gate table, logic table, to the AND gate, you can see that they are pretty much inverted. So here you have all the outputs off and only one case where the output is on. And here you have only one case where the output is off, and in all of the other cases the output is on. So this is interesting. Interestingly enough, in some cases, an OR gate can be replaced simply by a wire, because check this out. It turns on, or if both are on, they turn on. You need to turn both off in order for this to work. So let's stop the simulation. Let's move the chip, and let's just connect wires like this. And if we run the simulation now, it does the same thing. Anything that you do in here will turn on the LED, except when you turn both off. One reason why you might want to keep the component is because it works as a diode, meaning it will make the signals flow only in one direction. So if I simulate again and press this button, you can see that it will activate the LED, but it will not backflow into this input in here, which might be important, especially if this input comes from a microcontroller and you don't want this line to be blocked by the signal. And finally, we get down to the XOR gate. Also called the exclusive OR gate, which is the same as an OR gate with one exception. It doesn't accept when both inputs are on, because it's exclusive. It's either one of the inputs on will turn on the outputs, or the other one. But if you turn both at the same time, it's not a single option, so it turns off the output. You can think of this, I use this example many times, like trying to determine where someone is. Is this person in the kitchen? Yes. Is this person outside the house? But you cannot be in the kitchen and outside the house at the same time, so because this is false, right? Okay. Let's do a short example here, and then we will go to a more complicated example, and hopefully you will understand fully what those things are about. So this is what some people call a gate enabler. It's simply a AND gate. And what this does is, let me make sure that this simulation is running. If we try to output signals, this is just a button. So this LED is supposed to be blinking. It doesn't do anything. But if we enable this bus, now we can send signals through. So this is one very interesting way of using this thing, because you can have multiple systems trying to output something to a device, but then you can turn on and off those buses using an AND gate, and then it won't be able to send any signals. And the reason why I'm using this in here is because we are now going to build an example together. So now that you understand how a enabler circuit works, we're going to try and build a little project together in here. So what I'm going to try to do is to emulate the functionality of an XOR gate using other simpler gates. All right, so let's maybe copy some of those guys in here. So let's copy the switches. I think I will use the OR gate, the basic OR gate in there, because as I told you, the XOR gate is basically an OR gate, and that will have also an output, maybe here, and because I know that this is going to require more space, and this is where we can start things off. All right, so let's remember again. So a XOR gate will activate in this case, also in this case, but if we turn both on, this is not supposed to activate. So basically we're trying to build an OR gate with one exception, and in order to treat this exception, we are going to use the gate enabler concept. So let's copy, let's go out of the turn off the simulation and copy this component. So we can use this little icon to invert the gate, and then that's what we have in here. Let's also copy a switch in here. So now we have an enabler here that we can control using a switch. All right, so let's run the simulation again. So this is a perfect case, another perfect case, but when we have both inputs activated, well, actually, I think I need this to be activated. Sorry, guys. All right, so this works, but when we have both inputs activated, we want this switch to turn off, and this will emulate a XOR gate perfectly. All right, so let's try to control this enabler now. The way I want to do this is by doing something with those two signals. So when those two signals are active, we do something. We know a gate that does that, right? And it's an AND gate. Another alternative is to use a NOT gate. Let me show you how, so that you can learn more from this. I think I can pull those. Also, we'll need a bridge. So unfortunately, in this game, we only have vertical bridges. So we can connect the input to this guy and also to this other guy. Here, we'll merge the signals, and then we won't need this guy anymore. And then we can connect this like so. Okay, so this is going to be our enabler this time. Let's see what this does. If we turn on the simulation, because those inputs are turned off, the NOT gates keep the enabler enabled. So if we turn on any of those, the signal goes through. Same for the other case. And when we turn both on, then the two NOT gates, there are no NOT gates available to keep the enabler enabled, so the signal doesn't go through. And this is a perfect emulator of a XOR gate. As I mentioned in the beginning, it's also possible to use AND logic in here. So let's turn off the simulation, get rid of those components, and replace them with yet another AND gate in here. And this is another interesting thing to explain. First, you cannot connect a component to itself, so you cannot have this. But you will notice that there is this little dot in here, and what this represents is an inversion. So every component has an output right here and an inverted output. It's the same logic inside, but it's the same as having a NOT gate right here, placed right here. Okay, so let's see what this does. Okay, simulation is running, none of the outputs are turned on, and because there's no active inputs in here, we just output a true or positive or 1 in here. If we turn on any of those, this doesn't interfere, because remember, this is an AND gate. It requires 2 inputs to be active in order for it to take any action, which is exactly what we're looking for. So when both inputs are on, finally the AND gate has to make a decision. So remember this little table in here, and because we are taking the inverted output, it saves us from having to use another NOT gate at the output. We disable the the enabler or the gates enabler or the signal enabler, and yeah, signals can't flow, and then we can emulate yet again, once again, a XOR gate. All right, guys. So I think that if you were able to understand those examples, you were going to be fine. So sometimes it's kind of complicated to use those gates for complex examples, for complex puzzles, but at least with the basic, you can start composing your own very complex compositions of logical gates and do crazy solutions. So that's it for now, guys. Thank you very much for watching. Don't forget to leave some feedback and see you soon. Bye.